Every revolution has a spark. For the modern biogas industry, that spark was human waste. Welcome to the Poo Boom, a period of wild innovation, bold experimentation, and groundbreaking success stories that laid the foundation for today's anaerobic digestion technologies. From streetlights powered by sewage to tanks that turn sludge into gold, this is the story of 1876 to 1930 and why it should inspire everything we do today. Before 1876, waste was a public menace. Cities overflowed with cesspools, disease was rampant, and sanitation was a nightmare. London's infamous Great Stink of 1858, when the smell of untreated sewage overwhelmed the city, forced Parliament to flee and prompted urgent sanitation reform. Yet beneath this chaos was a biological process waiting to be harnessed: anaerobic digestion, the natural breakdown of organic matter, releasing biogas. But it would take a scientific leap to recognize the true potential. In 1876, German chemist Felix Hauptsaler made a groundbreaking discovery. Acetate in sewage sludge could be converted into equal parts methane and carbon dioxide. This was one of the earliest scientific confirmations of what we now know as anaerobic digestion. It wasn't just curiosity, it was chemistry proving that waste held energy. With that, the biological potential of sludge became a topic of serious scientific interest. The 1880s witnessed a rise in gas-powered technology. The internal combustion engine, then running on producer gas, was rapidly evolving. Though not yet fueled by biogas, these engines demonstrated the feasibility of gaseous fuels in powering the mechanical age. The bridge to renewable biogas was forming. In 1895, the city of Exeter, England, began using gas from sewage to light its streets. In 1897, biogas made its way to the Matinga Leper Asylum in Mumbai, India, where it was used to provide lighting as well. These pioneering installations demonstrated the practical and global promise of biogas, from Victorian England to colonial India. By the turn of the century, biogas plants were spreading across England. Cities recognized their dual role in waste treatment and energy generation. Methane, once just a byproduct, was now a municipal asset, lighting homes and powering early infrastructure. In 1904, Dr. William Owen Travis introduced a visionary design intended to improve upon existing contact bed systems, which were prone to clogging. Installed at Hampton, England, the system functioned as a multi-stage septic tank. The goal? Efficient separation, sedimentation, and hydrolysis, laying the conceptual groundwork for modern two-stage digestion. Though the original Travis plant functioned only briefly, and only one more was ever built in Norwich in 1909, its influence was real. His successor, Karl Imhoff, went on to develop his own version, the now famous Imhoff tank. Travis's ideas may have been overtaken by others, but his contribution marked a critical shift toward engineered digestion processes. While engineers built systems, scientists like Dutch microbiologist Nicolaas Louis Songen peered deeper into the microbial world. In 1906, he enriched two distinct acetate utilizing bacteria and discovered that methane could also be formed from formate, hydrogen, and carbon dioxide, uncovering core pathways in methanogenesis still taught today. From 1906 into the 1930s, England saw another round of bold experimentation. Large-scale sludge lagoons, passive anaerobic digesters, were trialed. Though initially plagued with failures, success came in 1911, proving that even nature's pace could yield scalable biogas systems. Parallel to the success of the technology's rapid evolution, the field of microbiology was leaping forward as well. By the 1930s, scientists like Buswell and Hatfield identified key anaerobic bacteria and defined the environmental conditions needed to maximize methane output. Their discoveries shaped the modern understanding of what makes a digester thrive. From septic tanks to city lights, this era saw a cascade of discoveries that redefined waste. These weren't just scientific events, they were technological detonations, a boom echoing into our century. The lessons of the Poo Boom live on. Today's digesters still rely on microbial pathways identified by Songen. They operate on design philosophies seeded by Travis. They aim for community scale impact, just like in Exeter. If we want to innovate, we must remember we're not starting from scratch. We're continuing a legacy. We owe our roots to fearless thinkers, bold builders, and microbial masterminds. Their work turned waste into wonder. Now it's our turn to rediscover, reinvent, and reignite the next boom.